Thanks everyone for coming. Today we've got Martin from the University of York. So nice agreed to give us an in-person seminar about reservoir computing, which is something I don't know anything about. So looking forward to it.
Fantastic, yes. So hopefully you will hopefully know what reservoir computing is afterwards. So good. Okay. Hello. Thank you for the introduction and also for the invite of having me. It's actually the first time in 18 months or so that I do a live one. So it's great to see everybody 3D. Good. Okay. So reservoir computing with physical substrates. This is kind of the big topic, and because I know that for some it might be kind of a new concept, so I'm kind of picking up a little bit, and what I'm gonna go through is kind of the whole stack of what a reservoir computer is, and actually what I mean by physical substrate and how to make one hopefully one day. This is working. No. Yeah. Okay. So what's a computer anyway? Yeah. I mean, most people, if you say the word computer, and they go beyond the desktop, they may think of a kind of a mobile phone. Oh, this is reflecting the laser, isn't it? So they may think of mobile phones, little robots, embedded systems, or HPC resources, desktop computers. If you ask me what I think of what a computer is, or what an unconventional computer is, then I think more like of systems like you see on this screen. So there are kind of some which are quite funky. So you have like biological systems. This is kind of a fungus network solving a kind of a routing problem. And then you've got analytical systems over here. You've got behavioral systems. You've got mathematical systems. Have you heard of cellular automata and things like that? Okay, that's fine. And then we have chemical systems and DNA computing. I'm sure everybody has heard of. This would be an unconventional computer. We've looked at carbon nanotubes, which are kind of structured networks of carbon nanotubes that we're computing with, magnetic materials, and biological models, chemical models. And it all started off with a bucket of water. Actually, this is where the kind of maybe the word reservoir was inspired from. So you have a bucket of water, you excite the surface, and then you put a camera in it, and you basically identify what just dropped into the water, more or less. It's a little, I keep that up there, that's fine. So, but not many people may think of these actually as computers. So why am I interested in unconventional computers? Because digital computers are power hungry, they're fragile, they're hard to interface to the real world, and they are quite resource intensive when you want to make them. Yeah, so I mean, I like shiny toys, yes, and I stand guilty as charged, but it's actually quite concerning in a way the amount of energy, the amount of raw materials, and also rare earth materials, and all of these things that actually go into making these computers. So if you have a more natural way of making computers, that would be a bonus as well. So unconventional computers, in contrast, this house believes anyway, so they are energy efficient, robust, so the opposite essentially. They're naturally part of the world, and they are therefore resource efficient as well. Yeah, so if you picture this, unconventional computers and classical conventional computers, I would draw this picture. I'm not advocating getting rid of digital computers because at the end of the day, they are ubiquitous. Yeah, they are used for everything that we currently do. And what I am advocating, thinking of a stack where we push as much compute as possible away from the digital computer and to the edge, essentially, yeah, and using unconventional computers at the edge. So you can see here, this is kind of a picture of kind of looking at computers through a lens of kind of dynamics. Yeah, so if you have at the bottom of a familiar digital computer, it's actually all that we do to the silicon. We process it, we make it groan and complain and get hot. Yeah, if we want to do computation with it, we force it to flip digital bits essentially and do Boolean logic. So we create energy wells. So we use a clock, and we push the system from state to state. And it's all imposed metadynamics in that sense. Yeah, so Boolean logic. So if you then go up the stack here, we have to do certain things to reach our computer from the real world at the top with the inputs and outputs. We need sensors and actuators. We need processing. We need different modalities. We need we need to translate between different timescales when we do sampling. We need to do signal transduction, and for all of these, we have entities or computers or machines that basically do that for us. But if you go closer to the real world, essentially, and you would have an unconventional computer, then you could achieve computation purely input-driven. Yeah, so you would operate on energy transients rather than having to invest every step you take a lot of energy to push them from well to well. Then you have this transition region in the middle. So why now? Why is it interesting, particularly now, or actually, or maybe the past 10 years and into the future, to look at these kinds of unconventional computers? There are two drivers. One is miniaturization, and the other one is diversification. Yeah, so my other leg is in kind of electronics, and people always show a slide of Moore's law. My students told me, take that slide out. Everybody's bored of it, and I did. So the message I want to give you anyway is miniaturization and diversification. Yeah, so we have miniaturization in our classical computers with all the benefits and kind of drawbacks that it has. But at the same time, we're living in a time where people explore a diversity of materials to actually build computers. And they're the ones that I actually would almost call classical already, so which is kind of memristus, for instance, and things like that, or DNA and polymers are maybe the more wacky ones. So we have these two axes, and we want these to enable a whole host of new applications. Yeah, so all of our applications which are not number crunching in a data center have to do with interfacing with the real world, with people, yeah, or solve like some problem. So you have these different areas where you can create sensors, embedded systems, smart devices, and all of these things. So health, transport, security, energy, communication, infotainment, and so on. The reason I'm putting those on is just to show you, these are kind of the two expressions that come out of the electronics people. There is this expression more than more, which means non-classical computers, diverse systems. And then there's like more, which is the miniaturization. Yeah, make our computers more capable, more efficient, cram more functionality into them. So typically, I mean, we are kind of aiming at solving some of these problems with our computers. But if we want to build a whole new generation of computers, we have to use benchmarks for the time being. The ones that we're using is essentially time series prediction, classification in time. So this is not static classification. This is kind of all on dynamical problems, essentially time series problems. We have control systems, robotics, and things like that. So this is kind of the picture that you get if you want to do an application with your computer. Then you have to have some input and output. You have to do signal transduction. You have to do some sort of encoding, and then you have at the very bottom you have some sort of substrate that does the computation. Yeah, so whenever I say substrate, then I kind of refer to this bottom thing. And you can see I've kind of listed binary, I've listed kind of other weird symbols that I thought look funky. You have the brain there, that is always cited as being super great at low power computation. But of course, it's a completely different type of computation than our digital computers are doing. Yeah, so it would be a bit hypocritical to stand here and say I want every computer to be like the brain, because I mean some people do, but it's a bit silly in that sense, yeah, because it's a very different type of computation, and we need both types of computation. So before I now go on and motivate the first half of my title, which is Reservoir Computing, I want to tell you a little bit, I want to give you an example of the history of where this field I'm working in kind of comes from. This is only one of many historical spokes, yeah, and this is essentially from the electronic side. There are also biologists, DNA computing would be another spoke, yeah, so this is one of these examples, and chemical as well. So quite a long time ago, actually, I keep showing this to the wall there. So quite a long time ago, there was a guy, Gordon Pask, he was a chemist. He filled this big vat with kind of a sulfuric acid, and then he put electrodes in and evolved voltages or currents along those, and then the metal dissolved in this acid kind of formed this kind of weird structure and he evolved it to be an ear. So that was quite remarkable. So actually, he was one of the pioneers of this kind of thinking. Yeah, so he used this latter thing, and he managed to evolve by modulating currents a structure out of kind of iron, I guess, in an acid to be susceptible to sound. That's quite cool. So then nothing happened for a while, and then there were these people looking at conducting polymers. Other people looked at FPGAs, but not using them in the conventional sense, but trying to use them as analog substrates, basically driving them in a regime they're not intended for or designed for. And other people actually said, let's get rid of all these substrates and just put a lot of switches on a breadboard, analog switches, and see what an optimization algorithm can get those switches to do. Now, 10 years later, people started in the electronics side of things, started to say, okay, we want to make these systems a bit more defined, a bit more controllable. And then this idea of FPAAs, FPTAs, or liquid crystal displays came along. So you have a component that you can reconfigure, reprogram, that you kind of know the structure of, but that behaves in a kind of an analog, nonlinear way. Yeah? But it's more defined in the sense that you kind of you can explain maybe a bit better of what you're doing to the system. And then 10 years again later, people then started to push this forward, because obviously there are limitations with this kind of technology that was here in the 2000s. So people started then to look at novel nanomaterials, so like liquid crystal, but this time like as droplets on an electrode array rather than a pre-made liquid crystal display, gold nanoparticles or carbon nanotubes. Setups that look like this. So you have your material here, you have it on a gold electrode array, and then you interface it to a computer. Again, this idea of having an evolutionary algorithm or an optimization algorithm that then gets this material or configures this material to do something was still pretty much there. And there were various projects that are listed here, basically building this up and looking at this. There is a big problem with that, or a big limitation with that, which is precisely what we with our current work try to overcome. Yes, I'm going to tell you what it is in a minute. So the picture is maybe less exciting than a blob of nanotubes in this case, of what we are driven by, but I'm explaining this picture in a second. So the issue is that if you are going down this historical trajectory, then you find yourself in a kind of almost like a hole where you're only focusing at the bottom. You're saying, I have a funky material, I want to use it as a computer. So you have a physical system, you want to solve a problem with it, so you prod it somehow, electrically, let's say. It's a physical system, and you want to do computation with it, so you have to wait for a bit. A physical system does something, sends it into a new state. And then you look at the system and you read the solution. You expect to read the solution out. The problem is that the whole top part of this kind of computing diagram is kind of almost ignored, because you need to be able to instantiate your input in the system. You need to be able to read out at the end, and you have to have some sort of model of what you are actually computing, which is kind of the abstract level here at the top. So the current, well, this is in fact also how classical computers are built. Yeah, so the top is Boolean logic, instantiation is analog to digital conversion, digital to analog conversion, and the bottom is a silicon substrate, for digital computer. And we have Boolean maths, and if you can make the difference between going from the problem to the solution this way or that way, you can make that difference small, then you have a good computer. Yeah. So the issue is now in these first or early generation material computers that people always looked at a specific task. So because obviously a digital computer has some sort of generality. A Boolean computer can compute any computable Boolean logic program. Yeah? So it is constrained, but it is fairly general. But people looked at specific tasks, so that is in a way constraining. And then instantiation and decoding, there's a lot of, in all these systems, there's a lot of clever engineering going on, where people apply a lot of brain and think like, how do we probe this material? How do we interpret what the material is telling us? And this has been done to an extent that what you get from the material, it's basically used as a glorified lookup table. Yeah. So if you spend all your effort in the encoding and the decoding, then your material doesn't actually have to be that good at computing. Yeah. So, and you have to be kind of mindful of that. So this takes me now to these unconventional substrates and what the issue is with them in a way. So they promise to be ultra low power, parallel, robust, efficient, and so on. They are a more natural fit to kind of maybe dynamics of the real world or more biological kind of models to begin with because of the energy transient in the energy wells that I was talking about before. But the problem is they are not very well characterized or understood, even by material scientists. Material scientists have they measure higher level properties of materials, sheet resistance, whatever, but I mean, I don't care about that. I want to use it as a computer. Yeah. So these detailed dynamics are not well characterized or understood. And the maths to fully describe them is either too abstract or it's too hard to compute. Yeah, it doesn't scale. Because if you have to run an atomistic simulation of this blob of carbon nanotubes, you're going to be there for a very long time. Yeah. And then it's only applicable to the specific blob that you have specified in your mesh. So you don't want that. So the questions that we then start to ask is how can we tell whether this particular substrate is a good computer? Is it better than the other substrate? If you create two blobs of CNTs, is this one better than that one, and why? Can we predict how well it's going to compute? Yeah, before we actually put it into our machine and deploy it and see that it's really rubbish. And finally, also, how can we change this, or how can we design with these materials to be a better computer? Is there anything that we can do to them that they become better? So what we need for that is a suitable computational model. And the model must capture the dynamics of a specific material or a specific substrate. The problem needs to be instantiated within the substrate, so there must be a way of actually encoding it in the substrate without spending a ton of engineering equipment to do it. And we want to be able to apply a blob to many different problems, not just a specific single one. And we want to have, ideally at some point, this blob to be kind of affectable to be able to kind of configure it for different experiments and for different designs. Yeah. So this leads us to reservoir computing. Reservoir computing is a dynamical system, a subset of dynamical systems. It has a large, rich state space. It's based on echo-state networks. So the theory is kind of available. So the blob in the middle is the mathematical model it has been conceived using an echo-state neural network. Yeah, and this is the whole theory is based on that in reservoir computing. Now the beautiful thing about it is now that you have, contrary to kind of how these systems usually work, where you have to kind of maybe in deep nets where you have to propagate through the whole network and you have to have knowledge of all the weights and things like that, so you don't need that. You can treat this blob in the middle, I'm deliberately using the word blob again, as a kind of a black box, and you only need an input layer and you need an output layer, and you need to be able to tap into a number of places in that black box, and then you can use a linear regression to solve your problem. Now this sounds too good to be true, but of course there is some conditions. So this black box, this reservoir in the middle, has to satisfy certain conditions. So it has to exhibit some, if you drive it with an input signal, it has to exhibit some specific dynamics. So it cannot just be a dead lump. It has to have some memory. So if you put in a sequence of signals, it cannot just immediately forget the first one and then before you put the second one in. So it has to have some sort of memory capacity. Be aware that the substrate, the material substrate where we apply this model to, is not an echo-state neural network. So it's a computational model. It is a substrate that we can manipulate in such a way that the reservoir model describes its dynamics, but it does not make it a neural network. Yeah, it does not make it an echo-state neural network. But RC captures the dynamics of the substrate, And the most important thing that I need now to go forward is reservoir computing can be trained on tasks, like the model, I'm talking about the model now, but it can also be evaluated on task-independent metrics. Yeah? And these are related to the properties that I just said are necessary for this blob in the middle to be a reservoir and useful for computing. Yeah? So we have generalization rank, kernel rank is kind of a measure of nonlinearity. Generalization is a measure of how well it can abstract things from the input, and memory capacity is a measure for how well it can memorize things for how long that you put into it, etc. So we have metrics which are task independent. And this kind of kicked off this piece of work, which was in a way quite nice because we used a novelty search algorithm. So it's kind of a type of evolutionary algorithm. The inventor says it has no fitness function, but of course it has the fitness function to look for something novel. Yeah, so, but the point is we used a novelty search algorithm that basically says create a reservoir system in the model still, evaluate it on these metrics, so independent of the task, and try to fill as much of this behavior space, which is kind of abstract, more abstract than a specific task, as much as possible. And the theory, I guess, says if you can cover most space, then there is a chance that you can find one that is useful to solve any task that you want to throw at it. And on the right side, the right-hand side, you can see now the difference between the carbon nanotube polymer that we've been using to that point, up to that point, and then the bigger areas and a simulation essentially of an echo-state network with 50 nodes. And remember, the fill level tells you how good of a computer it is. And this is when we could for the first time measure how much better the echo-state network substrate, the simulation substrate, is than our little blob of nanotubes. So they're pretty rubbish, yeah. So, but it's nice to be able to actually verify it and quantify it. So, well, this kind of, they're not useless because there are actually problems that sit down here that you can still solve with them. But they're not, you know, if there is a problem that needs to be here, then you cannot solve it with it. Another advantage is once you build up this database of reservoir combinations, or sorry, reservoir configurations, then you can use a kind of a greedy algorithm on top of it, like a particle swarm optimizer or something like that. And then take these and quickly find the one that is best at solving one of your nonlinear time series problems. So Llama is kind of a benchmark that we often use because it's fully synthetic. Yes, you can have as much data as you want. It is designed to have a certain dynamics, certain nonlinearity, memory capacity. So 10 has a memory capacity of 10 time steps, 20 to 30. So it's you can generate. So which is quite silly, has no real meaning in the real world, I guess, but it's a convenient benchmark for measuring quantifiably, like your system. Then there are the lasers, FFP laser set, channel equalization, sunspot data, and so on. There are various other type of data that we use. But this is quite nice. This tool that allows you to now quantifying these reservoirs and their performance allows us to ask two other questions now. So we can investigate now reservoir topology. My end goal is to have a physical system, to implement something in a physical system. So one question to ask is, how much connectivity do I actually need in my network? How is there anything kind of structure this somehow? So what gives me the best performance? And what topology is best? So in this case, we've looked at rings, we've looked at lattices and toruses, whatever, all the stuff that we can find funky against funky shapes. And then we use an evolutionary algorithm to evolve the connectivity of this, and we measure the performance with the tool that I just showed you. And the finding is actually quite interesting because in this case, it's for example of a ring. So, and here you can see a ring with up to 1% of so-called small world connections added. So a ring would not have these that go to the middle. The ring would be connected to self and to the nearest neighbors. That would be a fully connected ring. And then plus 1% of these number of nodes essentially as small wire connections going through the middle. What we see here is actually the top shows you if you don't add these connections, so just like a pure ring, and you increase the number of nodes, it fills the space more and more and more, so the computational ability goes up. If you now start to add more and more and more of these small wire connections, there is actually a threshold of about 10% of the number of nodes, and if you go above them, you don't get any further gains. That was good news for us, because actually, you don't need a fully connected network to have a good computer. And I guess this is confirmed, of course, with like I guess traditional neural network research as well. But it is nice because if you ultimately want to make one, the fewer wires you have to put in at some point, the better. And this is basically, this is just, again, a comparison of all these topologies that I just showed you. So this is kind of topology 3 is a fully connected network. That is torus ring. The fully connected network is, of course, best. So the quality here is how well it fills this space and how much it fills of this behavior space. And you can see the ring is actually worse. So, but of course, the cost is it's bigger and it takes longer to train the model. So having now found all of these things leads now to the next question, which is different reservoir types. Because I just advocated cutting down the number of wires that you have to plug into your computer to make it work better. And now we are wondering, one of the drawbacks of the classic reservoir is you have potentially a lot of inputs and a lot of outputs. In the theoretical model, if you have a network with 400 nodes, technically you've got 400 output weights. Yeah, it's not a problem because it's a linear classifier, but you wouldn't want to build a computer necessarily with 400 outputs to get only one meaningful output. Yeah, so there is now a different type of reservoirs, which is a delay feedback reservoir. And the difference there is, as we got excited about that, because it kind of solves this multiple input, multiple output problem and transforms it into kind of single output, single input, single output problem by doing a kind of spatial temporal trade-off. So the way this works is, rather than putting in your input in various different places and apply some input scaling, you are modulating or multiplexing your input signal with a mask, and there are different masks, so you spread information in time. You've only got one nonlinear node and a delay line, that is essentially your memory. And this masking process creates a number of virtual nodes along this delay line. And the time multiplexing makes these nodes or the information content of these nodes interact over time. Yeah, so you have a virtual network, but you only have one input and one output, but you can use it and train it in the same way that a classical reservoir. That's what excited us about that. So here are some initial experiments that we did with that, mainly to do with the input masking. And again, we used the NAMA benchmarks and time series prediction benchmarks, and it all worked reasonably well. And we looked at offset and of the type of mask, a random weight mask, a real value weight mask, and a binary weight mask. And we found that basically no offset works best. And so this kind of how to basically use these delay feedback reservoirs so that they work best. But of course, the trade-off there is you have to potentially, if you want to calculate as fast as the fully connected reservoir, you have to run them faster in a way, because you're trading space for time. Oops. So here are some solutions, some results basically for the different combinations. So binary mask, real mask, offset, no offset, and this is for the NAMA 10 benchmark. And this is the normalized mean square error, and you can see that this case has done best. And we have done the control experiment where we randomize the input with a static mask, we randomize the mask with a single input, and we randomize both basically. And then we do a number of runs, and you see there's no there's no significant difference, which is good news. Yeah. So I don't want the system to be specific to a specific mask or a specific input. It's not the case. So that's quite nice. Yeah. So you can cut down on the number of internal connections, and you can cut down potentially on the number of inputs and outputs. So these tools allow, and these kind of findings with the abstract computational model allow us now to look again into different material substrates. So, and once we've evaluated materials, we can then again ask questions: how can we pattern them? Yeah, we can then go to a material scientist and say, we want this structure. So how can we achieve that? How can we pattern this? How can we design this to make them better reservoirs? There is also an idea about using sensors or actuators directly as reservoirs. There are people, there's a group in Canada who use MEMS devices, and they are essentially they're audio sensors, but at the same time they're using the vibrations of the MEMS devices as a kind of as a reservoir. So you sense and process at the same time. So that would be fantastic. This is kind of what I said about pushing as much as possible of the compute and inference to the edge, really, with these kinds of devices. So you don't have to collect the data and send it to the digital layer, but you can actually already do a lot of the computational load at the edge directly in a more kind of a natural, using the natural dynamics of what we've got there anyway. But of course, different materials have different timescales and different modalities, and this imposes other challenges when you then want to interface them, when you build a whole reservoir computing architecture. So what we did is we took an intermediate step before diving into materials again. We took an intermediate step. We prototyped systems using programmable analog systems again. And that is quite a nice prototyping platform, because an analog computer is kind of, well, it's shown to be able to compute any differential equation essentially that you want. It's flexible, versatile, we can control it, we know kind of how we can design with it. But we can still use our abstract reservoir computing model and apply it to it. So it's actually quite nice. And the second thing that this allowed us to do is kind of to derive some sort of methodology to actually go from a mathematical model to a hardware implementation of a reservoir with specific dynamics. So I can only give an overview of this, yeah, because feel free to ask me anything about it if you want to have a deep technical discussion. I'm also happy to do it afterwards. So this is how these chips look like. So we have 3 of these. There's a company called Anodyne. They sell these little analog configurable processors. They are analog signal processors. You have an 80s, 90s user interface for them, but you can also basically use C and interfacing with the programming interface. But what we've done here is you can essentially the bottom line is you have parameterizable analog functional blocks that you can interconnect and you can parameterize. In this case, we've built a delay line reservoir. This is why I was motivating these delay line reservoirs, because these chips don't have 50 outputs and 50 inputs, yeah, or 400 inputs, 400 outputs. So we need to use the reservoir type with a smaller input and output count, with smaller input output bandwidth. There are development boards, so we don't have to worry about that. We can focus on basically finding the circuit and finding the parameters of the circuit that give us a good reservoir, and then learn something from it. This then also allows us to say, okay, if we take an equation as a starting point, this is the form of a delay differential equation essentially. So you've got your nonlinearity here, you've got your input here, and then you've got your decay rate and your generation rate essentially. So it's just normal differential equation. This is a relatively famous one in my circle because it is the so-called Mackey-Glass delay differential equation. Mackey and Glass are 2 guys. They're actually medics or biologists, I think. So they came up with this model to measure blood cells as a generation and kind of destruction of I think it's blood disease, some blood disease. Yeah. So it's a predictive model that comes from medicine. But at some point, somebody thought, oh, I'll take this model and see what I can do reservoir computing with it. So what we then investigated is basically, can you kind of from this equation identify components that you need in your delay feedback reservoir, nonlinear node, integration, delay, block, yeah, the conceptual. Link it to the terms in your equation, and then go through this translation step, and then identify where you then need to do the refinement in order to make it implementable in analog hardware, and essentially construct a reservoir with these dynamics, the mapping glass equation. And that has worked. That is actually quite nice. And what you can now do with it is you can now go away and say, okay, the translation step identifies which bit does the nonlinearity, which bit does the delay, which bit does, and so on. And the refinement step is always the same. Yeah, so once we know how to do it for a given technology, then we can just pack that away and just apply it. And what we can then do is we can tune the nonlinearity and see whether there is an optimum within the configuration range. We can look at, again, at time series. So this is the output of the system and the target output and how it predicts the normal series. And again, we have the same benchmarks here. And what we can also do is we can explore, this is what we're currently exploring, these kinds of diagrams, which are kind of attractor diagrams or phase portraits of these systems as we're kind of sweeping different parameters. So we're hoping that we can maybe do something with these diagrams to kind of, so that we basically say, okay, if this looks like a pretty butterfly, then it's a great computer, and if it doesn't, it's a bad computer. I mean, it's just like, so something that there is theory available of tractor reconstruction techniques and things like that, but just currently started looking into this to learn more about the dynamics and how to basically classify what's good and what's bad in these computers. So this then actually, so this intermediate step using analog electronics is now using a technology that we can have available, that we can know how it works, and there is now a nice success, I guess, in the middle to kind of link it to the reservoir model to kind of make it parameterizable. Now we can take a leap and go to actual materials again. So we have collaboration with some guys in Sheffield, but this is an EPSC grant. It's now actually, it's just started actually in the middle of the pandemic. It's called MARCH, Magnetic Architectures for Reservoir Computing. It's always all about the acronyms, we all know that. So, and what these guys do, these are material scientists, we are the computing people, and they are creating these kind of arrays of nano rings, just a ferromagnetic material, and when you apply a magnetic field, then they go through different states and different magnetizations. So you can have like rotating domain walls, or you can have like all the domain walls become static and balance each other out. So they can have various different states, and you can read them out as a resistance, from that material. Yeah, so but that's material science. So they explain all that stuff to me. So that's fine. But what we want to do is we want to excite that material electrically and magnetically, and we want then to have the dynamics of these rings, and we want to use them for computation, in the same way that I just explained. Now, this is an interesting material. Why? Because it is structured. Yeah, and we have actually got initial evidence that you can use it as a reservoir. At the moment, it performs so-so, but the point is, in a way, we're not trying to find the best material at this stage, but we try to come up with a method of how to pattern this and understand what you need to do to a material like that in order to then make it better as a computer. The second material experiment or material collaboration was at York actually with somebody in physics, Richard Evans, and there was a student who they have a simulator which is kind of an atomistic simulator or like just above atomistic of a magnetic spin system, and we've used an anti-ferromagnetic system, so it's manganese platinum. So again, I'm not the physicist in this case here, but Richard tells me that antiferromagnets are great because you can actually manipulate them in certain ways. And you can see here again, this is the idea of domain wall forming. And this is a magnetic substrate excited by a laser pulse. And then you see the domain wall sort of polarization basically shifting around. And this is different to the same material when you just have a bulk and you see the domain walls forming of spin up and spin down. And when you pattern it in this kind of simple way where you have exchange only at these junctions, you get this behavior. Yeah, and this is already kind of quite cool. Because if we now, this is what the physicists do and get excited about, but they would then only basically look at this pattern, and the computing guys can then say, hey, we know all these algorithms that give us different patterns. You know, can we maybe sit down and think of some sort of generative approach, maybe to get a pattern, and then actually come back to what I condemned in the beginning, which is making chips, because maybe we can then just actually create patterns of these magnetic materials with traditional technology in that sense. And we've tried that actually. So we tried it on the robot as well. So not the materials yet. So this experiment is probably going to be, there is a big machine here with the material and the robot is going to be there, and it's probably going to be a Wi-Fi connection between them, which is like obviously the ultimate cheat. But this robot was actually quite nice because it had an anodyne board here actually underneath, so it had the analog substrates and with the delay and reservoir. And what we did here is we have a hi-fi, what we call hi-fi sensor from this robot, which is a LiDAR that has quite a good spatial resolution basically, and then around here are, I think, 5 or 6, I don't know, 8, what we call lo-fi infrared sensors. So the experiment that we did there is we trained the reservoir in such a way that we could train it on the hi-fi sensor, but then have essentially inference of the robot navigation with the lo-fi sensors. So this is all kind of about this is about probing basically. How can you integrate this into systems? How can you make these more efficient? Yeah, so how can you get this idea of kind of edge processing? Yeah. I mean, ideally we would then throw away the computer and have sensors that do the computation themselves, and then you just have to read the state and you know where to go. By just doing subtraction or something like that. That has worked quite well, but the robot was kind of moving around. I mean, it was not the experiment itself. What the robot did is not spectacular. Yeah, so I mean, it helps to avoid the block, but it did avoid the block, so that's good. And this leads me now to this kind of vision of almost like an edge computer or an edge processor, which is kind of general purpose. So this is kind of the architecture that we currently, we will have in a couple of months. The PhD students starting who will look at bringing these concepts together now, that I was just talking about, and investigate how it is possible to actually hook these reservoirs together. Because you can do it in a silly way again, by basically almost like the equivalent of an ADC or a DAC, where you train readout layers in between all of these, and then you feed these values into a new reservoir, or you can think about to have more dynamical links or delayed links or something like that between reservoirs and build up an architecture like that. So we have explored different types of reservoirs, like delay lines, randomly connected, but we can also impose structure, and we can have different materials, different substrates. So this becomes an investigation in a way in how it is possible to kind of link these multi-structure, multi-substrate systems together to achieve a more generically applicable reservoir computer architecture. Yeah. If you want to be, this is now in conclusion, this is the old trade-off, because if you want to be efficient, you cannot have a general purpose digital computer, because it's not going to be efficient over all cases. So you have to be specific. But if you're specific, then you constrain yourself, and you can only solve a subset of problems. And so how does this kind of hybrid computer architecture of an unconventional computer plus classical computer? Yeah? So I mean, as I said initially, I'm not advocating throwing away digital computers. I don't want to throw away a computer, but computers need to evolve. The computer architecture has not really evolved over the past 40 years, to be honest, in that sense. I hope I don't offend any DeepNet people, but I mean, all you're doing on your graphics cards is just digital computing. It's wasteful. Yeah. And this leads me to my conclusions. Not done such a bad job. Good. Nick will know that I'm always kind of known for not being brief, but this is just summarizing it all up, really. So the goal here is of all of these investigations in various directions: structure, computational model, computational substrate, how to bring them together, is really how can we design, evaluate, and apply these computational models, different substrates? How can we bring them together? How can we do the interfacing cleverly? Because we don't want to throw away our gains. Yeah, we don't. If you have a great, maybe let's say a great sensor that can do some implicit prediction as well, and you have the right modality, so you have a microphone essentially that can suppress noise by itself, for instance, like that. Then if you then get the audio data out, you don't want to, and you want to do some further processing, you don't want to then digitize it, yeah? Because then you kind of defeats the point. What we want is kind of architectures, and everything that's classical and digital we need, but we want to clock it as slowly as possible, yeah? And wake it up only when necessary. And it's kind of driven by this idea of really being careful and mindful of all these dimensions, yeah, like computational models, different substrates, how they link together, because we need some sort of abstract model to be able to say anything about how useful this process is here, and then also see that we're not getting too sidetracked, or that we do these two things cleverly, because otherwise, again, we kind of defeat, or we kind of negate all of the gains. Yeah. If we then have, this is kind of think of this as the ADC and the DAC, yeah, of digital logic. You've got sensors which are beautiful. You've got a digital computer which is beautiful, but a sensor is useless if you can't get the data out. The digital computer is beautiful, but you need to get the data in and out. So what you do is you put a big fat ADC and a DAC in the middle and clocks, and this is what costs. This is the cost of it. You know? And this is these two arrows that people often don't pay so much attention to. And with that, I'll just go to this big thanks slide. Actually, I tried to have a Zoom screenshot of all of us, but it didn't happen. So hopefully next time. So this is old-fashioned, the names of all the people, and this is mixed colleagues, RAs, and PhD students. So big thanks to them, because obviously they've done the hard work, and I'm standing here and waffling essentially. Good. Okay. Thank you very much.
Thank you. I will stop the recording.